In this example problem, what we're going to be talking about is Young's double slit experiment, which I have drawn here. And so how this works is you have light coming in to two slits. So you would have slit 1 and slit 2. And they're separated by a particular distance. And what happens is light can only pass through either slit 1 or slit 2. And if you put a screen here, what is observed is you'll have the what's called the 0th order, which would be a bright spot. Then you have a dark spot. Then you have a bright spot. And you have a dark spot. You have a bright spot, and you have a dark spot, and you continue on and on and on. Likewise, going down, you'd have a dark spot, you have a bright spot, you have a dark spot, and you have a bright spot. And so they're alternating between bright spots and dark spots. And what Young's double slit experiment does is it shows or it proves the wave nature of light. It proves that light truly is a wave. Now, if you go back to superpositioning, and if we have two light sources, right? If we have two light sources, so we can have this light source, and likewise, we can have another light source, and I'll draw it below it, right? Now, if you add those up, what you end up getting is you get a much larger light source. This is what's called constructive interference. So this would be constructive interference. Now, they don't just have to construct, or they don't have to interfere constructively, right? They could interfere destructively. So let's take a look to see what destructive interference is going to look like. So for destructive interference, this would be our first light source. This would be the wave. All right. Now, we can construct them such as this. If you add them up together, what you end up getting is they interfere destructively, meaning that where the crest is, there's going to be a trough, and where there's a trough, there's going to be a crest. And if you add these two waves together, they cancel themselves out, and you don't get any interference. It's destructive interference. As opposed to the first example, there what we got is we got constructive interference, where the crests lined up perfectly with the crest of the other wave. Now, in this one I just erased, what happens is we're off by exactly a half a wavelength. We're off by exactly a half a wavelength. And so in that case, you're going to get destructive interference. Now, that was with two sources. Now, here what you have is you have one source. However, the light from this slit can act as its individual source, and the light from this slit can act as its own individual source. And so these two lights can come together, and they can either constructively interfere, which is what you see in the bright spots, or they can destructively interfere, which is what you see in the dark spots. There is no light. Now, we can order these by such a way that directly straight here would be considered the 0th order. You go to the first bright spot from that, and that would be m equals 1. That's going to be the first order. Then that would be the second order. I could have very easily chosen the first order, but in this case I chose the second order. And what you can do is you can then find the angle for those a particular order. All right? Now, in this, so that's essentially how Young's double slit experiment works. And once again, it shows you that light is wave in nature, is wave-like in nature, because you can have constructive interference and you can also have destructive interference. Now, in this problem, what it states is that a double slit is illuminated by a Heine laser, a helium neon laser, whose wavelength, so the wavelength is equal to 632.8 millimeters. The second order bright spot fringe, or the second order bright fringe, is at an angle of 2.79 degrees. Now, the order, which is m, is the second. All right, so it says it's the second order, and our angle, our theta, is going to be equal to 2.79 degrees. So it's 2.79 degrees. And it wants to know, what is this separation? Well, the equation we're going to use for this is m, and then it's lambda is equal to d sine theta, where m is the order. So the numbers here represent the order, and we're looking at a bright spot. If we're looking at a dark spot, then this would be 0, this would be 1 and 2, 1 and 2. All right. Now lambda, as we've seen before, is going to be the wavelength. All right. D is the distance of the slit, or the distance between the slits. And then theta is going to be our angle. It's going to be our angle. Now in this case, we're looking for the distance. We're wanting to solve for the distance. We solve this equation for d, and d is equal to m lambda upon sine theta, which is equal to, we know our second order, which is 2, that is a unitless number. Our wavelength of the light, did I put, oh, that should be nanometers. Sorry, that should be nanometers, not millimeters. That should be nanometers. So that will be in nanometers. Now we can put this, so if we write that in terms of meters, our wavelength, that's going to be 632.8 times 10 to the negative 9th of a meter, divided by the sine of our angle, which is going to be 2.79 degrees. We do this arithmetic, and what we end up getting is we get 2.6 times 10 to the minus 5th of a meter. Now the problem wants us to put it in microns, and so there's going to be 1 times 10 to the 6th microns per meter. And so the meter cancels, and what we end up getting is we get approximately, we get 26 microns, or 26 micrometers. So from this experiment, we were able to determine, the slit, or the distance between these two slits. Once again, this is Young's double slit experiment. It's a remarkable, beautiful experiment. It once again proves the wave nature of light. If you have any questions on Young's double slit experiment or any problems pertaining to this, please let me know.